Computer Science and Engineering, National Institute of Technology, Rourkela. I will be presenting my work titled Instruction Control in Memory Sorting on Memory State Crossbars. This is the outline of my talk. So the first question which comes is why in-memory sorting? As we know that the traditional one-neuron architectures suffers a bottleneck for transferring data between memory and CPU. This degrades performance and increases power consumption for the data-intensive applications. In-memory computing can be an alternative approach to solve this problem. Sorting is an important data-intensive application where the big data, database and other applications require sorting. Sorting is a pre-processing step for many algorithms. Sorting within the memory will reduce bus transfers and cache misses. Memory star is being used as basic units for designing non-volatile memories. Memory stars can also be used to design logic circuits, which are called the memory star aided logic circuits. The memory star aided logic circuits allow in-memory computing. So the present work targets to use the memory star crossbars for doing the sorting in the memory using the memory star aided logic. Memory star was introduced in 1971. It is a two-terminal circuit and it is non-volatile. Its resistance changes from high to low and low to high depending on the direction of flow of current. It is compatible with the present CMOS technology. In 2008, HP Labs launched a titanium dioxide memory star which has the property of changing of resistance. A single bit can be realized using a memory star where its maximum resistance R off is represented as logic 0 while its minimum resistance R on is represented as logic 1 where R off is larger than R on. The memory stars can be used to design the resistive RAM, which is non-volatile, and also the memory star aided logic circuits. The memory star aided logic circuits or the magic logic circuits can be designed to realize any logic operations. The NOT and NOR logic memory star aided logic circuits can be installed within the memory crossbar, and this NOT
presentation, I would like to convince you that our proposed method is useful in stochastic computing. First, let me explain necessary basis for stochastic computing. Stochastic computing is an approximation calculation method using a stochastic number which represents the rate of the ones in bit strings. Stochastic number, in short SN, is a bit string to represent a value by the proposed probabilities of getting ones in bit strings. These three X, Y, Z are SNs. These three SN are 8 bits, and 4 bits out of the 8 bits are ones. These three SNs are different, but they are all represent 1/2. Next, I explain overview of the stochastic computing. We first convert conventional binary input number to SNs by SNG. Then we calculate a desired function by using SNs in STC manner. Finally, the real result of SC calculation is convert the conventional binary number by counting the number of ones in the result SN. Next, I explain in stochastic number generator. An SNG convert binary input number to stochastic numbers. An SNG consists of a linear feedback shift register and a comparator. This output 1 when y is larger than x and 0 otherwise. Next, let me explain arithmetic operations in SC. The SN generated by SNG calculated by these SC calculators. I would like to introduce a multiplayer and others as an example. This is a multiplayer in SC. These input SNs represent 1/2 for both x and y. The SN output by the AND gate represent 1/4 in value. The answer is 1/4 by 1/2 and 1/2. From this, we can confirm that multiplication has been performed. This is other in SC. The SN output by the multiplexer represent 1/2 in value. The addition value should be 1, but the addition by SC's multiplexer is 1/2 scale.
Meeting of graphene-based circuits. Authors are Subroto Das, Peter Pfizer, Shomo Pandit, and Devesh Kumar Das. This is the presentation outline. First, the introduction, then the discussion on graphene-based p-n junction, part distribution model of graphene-based p-n junction, followed by graphene-based gates and the estimation of switching activity, cascading of graphene-based gate, then the estimation of switching activity of graphene-based circuits, the rules and algorithms for switching activity reduction, followed by experimental result, conclusion, and references. Now, first the introduction. Graphene has several advantageous electrical properties such as high carrier mobility and saturation velocity. Graphene-based pass XNOR logic is an alternative logic style. In the subsequent slide, we will discuss this thing. Basic gates as well as circuit can be implemented with this type of logic. So in our research work, we basically implement the basic gates and circuit with the help of graphene p-n junction, and our goal is the reduction of the power dissipation. Now this circuit basically shows the graphene p-n junction, and it is constructed on a graphene sheet, and these two metal to graphene contact X and F are acting as the input and output respectively. E and H are the two back gates, and they are isolated from the graphene sheet by a thick layer of oxide. Here, if E and H are supplied with the same voltage level, then the two graphene region will have the same doping profile. As a result, a conducting path will be established from X to F. On the other hand, if E and H are supplied with different voltage level, then the doping profile will be different, and in that case there will be no conduction path from X to F. So this basically represents the equivalent electrical model of this. Now come here. So just to mention that if we supply E and H with the same voltage level, then a conduction path will be established from X to F. So in the input side, if we supply high voltage, then if E and H have the same voltage level, then we have the output as 1. So this gate will basically behave as a pass XNOR logic, and we will take this concept of pass XNOR logic and we will implement other gates from here. Now we discuss the power dissipation model. The physics of graphene is similar to that
methods will be shown. Photonic integrated circuits are the integration of electronic and photonic circuits on a single chip. And in this figure, some of the benefits of photonic integrated circuits are shown that satisfy the increasing demand of higher speed, low power consumption, and low power dissipation in current VLSI circuits. Further, to design these bigger photonic circuits, an automatic photonic design process is required as it is present in electronic design automation. In physical layout of optical circuits, an optimal routing of optical waveguide is very crucial and important step. And the routing of optical waveguide has these different type of losses where the bend loss depend upon the angle and the radius of the bend arc, and propagation loss it depend upon the length of the optical waveguide, and crossing loss is in the range of 0.16 to 0.2 dB per crossing. Here from this table we can see that the bend loss is decreased when the bend angle is increased. Hence, the waveguide having a smaller bend angle will have a higher bend loss. In the channel routing, a channel is represented as a horizontal path with the terminal list at the bottom and the top of its boundary. And here it is the representation of our channel grid where the waveguide follows a known Manhattan channel routing, and further the grid is divided into a number of cells where a cell is represented here. It has a height of h and width of w, and here theta, alpha and phi, these are the angles along the cell. These are the existing work in channel routing that follows a diagonal or non-Manhattan routing grid. And these are the channel routing parameters where track sharing and track reduction, they are reduces the total channel area, and bend reduction, it helps to reduce the total bend loss, and the horizontal restriction helps in elimination of smaller bend angle, which eventually
Testing audio.
Testing audio 1, 2, 3. Am I audible?
Next.
First of all, I would like to thank you for attending and presentation of our work. The title of our paper is Gain Stabilization Methodology for FinFET Amplifiers Considering the Self-Heating Effect. The name of all authors and application are listed here. Before giving you some facts and figures, I would like to give you some overview of our work. We are working in the analysis of various physical phenomena in FinFET devices and its implications on analog circuit. Since FinFET is an industry adopted and very popular device due to its excellent performance in comparison to the planar MOSFET. However, due to the confined structure and box layer beneath the active region, self-heating effect appears as a critical and important concern in these devices. Moreover, the gain instability due to the temperature variations has always been one of a critical concern in these devices in the analog circuit design. This issue becomes more complicated in FinFET amplifiers due to an additional temperature rise caused by the self-heating effect. So in this work, we have proposed a compensation technique to stabilize the gain against the temperature variations. We have demonstrated this technique for isothermal and self-heating conditions, and we have showed that the error in the gain can be effectively reduced by using the proposed technique. So this is the complete outline of our work. Since technology scaling improves the device performance in terms of speed, power consumption, cost, etc., however, there are several challenges such as social effects, which also comes with the scaling. So there are several techniques to overcome these limits. Multi-gate devices, strand silicon, high-K insulators are some interesting alternatives, and FinFET is one of them. FinFET is a thin fin-set body wrapped by the gate. It can be either double gate device or tri-gate device based on the thickness of the top oxide. So these are the advantages of FinFET device. It has better electrostatic gate controllability, reduced leakage current, improved short chain effect immunity, etc. So now we will discuss about the self-heating effect. Self-heating effect is a critical issue in FinFET device due to its nanoscale dimension and confined structure, which resists to dissipate the heat from the active region. Here we have shown the thermal profile of a 14 nanometer SOI FinFET. This is the source region, this is the drain region, gate, source extension, and drain extension region. It can be seen that a hot spot appears at the drain extension and drain junction. Thus, the carrier velocity and threshold voltage reduces due to the additional temperature rise in the device. So the drive current also degrades, as it can be seen in the output characteristics of the device. So the self-heating can lead to a serious device performance degradation and reliability problems. The gain in stability with the temperature becomes more critical in FinFET based analog circuit due to the self-heating and thus needs to be analyzed. Here we have shown the 3D schematic of a 14 nanometer SOI FinFET and the calibration of our simulation framework with the experimental data. Here we can see the doping profile of the channel and the extension region. It can be seen that a constant doping in the channel region, however a Gaussian doping in the extension region. The device dimensions of various device parameters are listed here. We have used the gate length of 20 nanometer, fin height of 26 nanometer, EOT of 0.85 nanometer, and these are the dopings and so on. So here we have shown the control plot of lattice temperature along the channel, and a hot spot can be observed at the junction of the drain extension and drain region. Here we have shown the profile of lattice temperature and carrier temperature and different region of the device. It can be observed that the peak of the lattice temperature exists in the junction of drain extension region and drain junction, while the peak of the carrier temperature exists in the edge of channel and drain extension region. So the position of hot spot is found to be located at the junction of drain extension region and drain region. Here we have shown the degradation in drive current at different gate voltages. Here we can observe that a higher current degradation at higher gate voltages, while it is negligible at 0.5 voltage and below that voltages. Here we have shown the power temperature curve at three different gate voltages, 0.4, 0.6 and 0.8 voltages. Here we can observe that the slope of the curve reduces by increasing the gate voltages. The slope of the curve is called the thermal resistance. So the thermal resistance reduces by increasing the gate voltages. It is mainly due to the increase in the head speed area. So the self-heating induces around 16% current degradation and 82 Kelvin temperature rise in the device at higher VGS, means at 0.8 voltages.
When we are going live. ठीक है, Q&A लाइव है. अभी हम ऑडियो भी टेस्ट कर रहे हैं, और क्या Q&A के टाइम पे पीछे ऑडियो आती है?
यार ये आती है
श्री टाइप करो ना बाय हैंड
भी कर लिया.
और दूसरी चीज फिर मैं यहाँ से शेयरिंग मैं जरा सा कर्सर लगाता हूँ, मैं वो लेके आ जाता हूँ। जब वीडियो खत्म हो जाएगी ना वहां पे बिल्कुल लास्ट वो पहुंच जाएगा, तो आपकी वीडियो रुक जाएगी। उस टाइम पे मैं बैनर स्टार्ट कर दूँ, तो साइड में बैठना, ऐसे बैठना कि मैं बैठूंगा, आप बैठना, फिर शुभता बैठना। ठीक है, क्यूएनए चल रहा है। नेक्स्ट क्या है? क्लोजिंग सेशन, तो इसी के अंदर हो जाएगा क्लोजिंग सेशन, एंडिंग सून। कितने बजे आना है ये?
participants of this conference will be better than the earlier editions, and I hope that the feeling is that the quality of papers continues to improve the way it has improved in the earlier years, and the level of participation